Hello, this is Chris Reed for mobile math tutoring, and we're going to do some fun problems related to math, how it can be applied to physics, and some hypothetical problems. The gravity constant has units of Newton meters squared per kilogram squared to make it consist of figuring out the gravity force of between two objects. Say we'll start with two objects. You got M1 and M2. And what's the gravity force? And just say force equals gravity constant times mass 1 m2 over r squared. And the units have to be consistent with here to get force, newtons. However, we could simplify this g to make it where it's easier to understand. And the way to do that, newtons has units of kilogram, has units of kilograms, meters per second squared. Okay, and what we want to do is just say G has units of, say, substitute for newtons, say kilograms times meters in the bottom, and then seconds squared times meters squared over kilograms squared. And it turns out you could do some simplification. The kilograms drop out here, and then you get down to 1. This is where algebra can be very useful in verifying units and just make, algebra 1 more interesting. Let's apply it to physical units. So therefore, G would have units of meters times meters squared. You got meters cubed per kilogram times second squared. And you know what? And there's this hypothetical name people may call this term, meters cubed per second squared. Maybe a gravity unit. Some people may throw in that phrase per kilogram, and that becomes your units. So when you simply multiply gravity constant times mass, you got meters cubed per second squared. And that's actually related to the accelerated volume rate of change, the second rate in which the volume increases or decreases. That could maybe show some light on how gravity works based on a compression of space in which we feel this thing we call gravity. Now, here's a hypothetical formula a guy named Thomas Bearden came up with, how gravity potential is equal some kind of a constant beta times the divergent of the magnetic potential field. The key is, want to figure out what units would that contain. We know that beta has units of meters squared per second squared. And we also know A has units of kilograms, meters per coulombs times second. That's actually the momentum with charge, like the momentum per charge of a moving massive particle. But if you take the divergence, like taking the derivative, that would take. So when you take the derivative of A, that would have units of kilograms, because the m's would drop out, times seconds. Okay, now with that being said, what would beta be? You could just divide it out. Beta, you just solve for beta. Just beta, therefore, would have, of course, meters squared over seconds squared, and times just the reciprocal of this, over that, times coulombs times second over kilograms. And it turns out these seconds drop out. You got here second to 1. You got coulombs per second. Beta equals coulombs per second times meters squared per kilogram. Well, coulombs per second is simply amps, which is current. So therefore, beta would have units of amps times meters squared per kilograms. Kilogram. That would be your units for the beta, and to convert the divergent of the magnetic potential to a gravity potential, which has units of meters squared per second squared. So that completes the proof relating mathematics to this fun problem, physics. So this is Chris Reed, ready to sign off.